My name is Shanda,
And my name is Anne.
and this is our prototype of innovative technology. We focused on ways of altering flow through a pipe. The application we looked into improved the flow in storm drains and sewer systems. This could prevent flooded sidewalks, roads, parking lots, and yards, while increasing the speed and lowering blockages in the system. This will help prevent damage to buildings, pavement, and pipes, all while increasing the flow rate of the water. We found that mucus a barracuda produces creates an increased viscosity around the fish, effectively lowering the turbulent flow and therefore lowers the energy needed. Most pipes in the storm drain and sewer systems are made out of materials such as concrete, steel, and cast iron, all of which have very rough surfaces which increase turbulence. This also uses energy from the system. So our goal is to decrease the turbulent flow while increasing viscosity as a way of lowering friction and reduce the energy needed to move the fluid by having less energy used throughout the system.
So for our method, we utilize the Renaissance boundary model. Our student learning challenge, as previously stated, is to improve flow through stormwater and sewer drains. For our organizational tools, we looked at fluid mechanic topics and equations. For our learning cycle, we focused on barracuda mucus having the potential to reduce viscosity of surrounding environment. For our resources, we utilized fluid mechanics and related classes along with our sources. For our LES, we looked at related equations, and specifically, we looked at linear versus turbulent flow. For our prototype, we want a material that can be sprayed onto pipes but does not interact with passing fluids. Here we'll look at some of our important calculations. First, we want to determine mass flow rate, or how much fluid is moving through our pipes in a given amount of time. Next, we want to look at 1- and 2-dimensional flows. We want these flows to be uniform throughout the pipe. We also want to determine deformation rate, which is the shear stress that's experienced by the fluid passing through the pipe. We also want to consider non-Newtonian fluids. These fluids have a higher viscosity than fluids like water. For our considerations, we want to look at laminar versus turbulent flow. For our model, we want to take a turbulent flow and turn it into laminar. This is because laminar flow has a Reynolds number less than 2,300, and it has limited mixing between layers. The velocity gradient at the wall is also lower, along with lower shear stress.
The market we are trying to target is anyone involved in the maintenance of storm drains and sewer systems. Because of this, our goal is to show how a less turbulent flow through the pipes can lead to less issues in the future. We want our prototype to be thought of as a way to help keep the system clear of any issues. Eventually, our prototype may be used in other applications, such as in labs where a laminar flow is needed. We also did a SWOT analysis of our prototype. As listed, we do have less mixing and less backups while using less energy. Yet there is some issues stopping us from being able to apply it to every case, as there will be an uneven heat transfer or a non-uniform mixture as separation occurs, both of which need mixing to correct.
For the application of this material, we want this material to be sprayed onto the inner walls of pipings. This material can be used on either existing or new pipes, due to stormwater and sewer pipes usually being big enough for the application to be easily carried out. For our conclusions, we see that pipes with a coating of viscous material that does not interact with material flow can provide a method to decrease turbulent flow. This decrease in turbulent flow would improve flow through stormwater and sewer pipes, therefore causing a decrease in flooding on sidewalks, roads, and parking lots. It can also prevent slow flow in sewers and water pipes, along with preventing blockages caused by turbulent flow. Application of this material can also decrease noise in pipes, decrease air resistance, head loss, and prevent cavitation, which would increase the longevity of these pipes. Decrease in turbulence can increase the efficiency at which material can be pumped through pipes. This would decrease the amount of energy and the amount of costs that go into operating the system. Material for this application can be applied to either new pipes or existing pipes by being sprayed onto the inner wall of the pipe. Most sewer and water pipes are large enough for this application to be carried out easily. Thank you again for joining us for our presentation.